All right. Does this work? Hello, everyone. Thanks for joining session 15. I think we'll get started. It's glad to see so many enthusiasts about management strategy evaluation here. So we're focusing on using MSE to establish robust fishery management in the changing ocean. While we have a minute before we're switching over to the next talk, I thought I just would introduce the conveners of the session. My name is Lisa Kerr. I'm at the University of Maine. Desiree Tomasi spearheaded a lot of this planning for this session. Desiree is at NOAA's Southwest Fisheries Science Center. We also have Karen Barcelo, who contributed from Oregon State University, Beth Fulton from CSIRO, Isaac Kaplan from the Northwest Fisheries Science Center at NOAA, Sonia Sanchez-Maruno, who is here with us today, from ASD, Robert Thorpe from CFAS, Cassidy D Peterson, who's here with us today, from NOAA's Southeast Fisheries Science Center, and Alfonso Perez Rodriguez from the Spanish Institute of Oceanography. So, diverse group, all interested in sharing more about MSE, and so excited so many folks have contributed some nice talks today. So, with that, I think we'll move to our next speaker. So we have Cassidy Peterson presenting today, Exploring Climate Readiness of Fisheries Management Procedures in the Southeast U.S. Atlantic. So thank you, Cassidy.
Thank you. So thank you for having me. I'm happy to be here. My name is Cassidy Peterson. I'm from the Southeast Fisheries Science Center at NOAA Fisheries. And I'm going to be talking about exploring climate readiness of fisheries management procedures in the Southeast U.S. Atlantic. I want to acknowledge all of my co-authors, of course, and I also want to start by acknowledging Blue Matter Science for their development of the Open MSE tool, which we used in this example, and also a tremendous amount of foundational work that Nikolai Klebansky has led, and some of that information can be found on these GitHub links. The GitHub link for this project is here. There's some more results up there. The code's a little messy. I have to go back and clean it up, but it is there if you're interested. So the motivation for this study really centers around the idea that climate change is threatening the assumption of stationarity that's inherent in a lot of our fisheries management decision making. So it's important to understand how our current management strategies perform in the face of climate-induced non-stationarity and develop alternative or test alternative management procedures where possible. I don't need to explain this to you, but MSE is, of course, the best framework in which to test this research question. So we did an MSE explicitly to explore how model-based and empirical management procedures perform for some case study species in the Southeast U.S. in the face of rapid climate change. This was a desk MSE, so we had no stakeholder input. And we followed Andre Punt's empirical approach of evaluating uncertainty to climate change or non-stationarity. So this is where the mechanistic link between environmental changes and scaling that up to stock-wide productivity is not addressed. We just impose some broad, plausible impacts of climate change and monitor how the management procedures fare through those changes. We looked at 3 commercially and recreationally important species in the Southeast U.S. Atlantic. From the fastest growing to the slowest growing, we have vermilion snapper, black sea bass, and red porgy. They're all not overfished with no overfishing, with the exception of red porgy, which is overfished. As Jose mentioned in the last talk, we have our sort of empirical stock assessment being the framework for our base operating model, with stationary projections into the future. We then imposed some non-stationarity in the future. We looked at episodic high natural mortality events. We imposed regime shifts where the mechanism of that shift was through an increase or decrease in the magnitude of recruitment deviations, a shift in age 0 natural mortality, and a shift in the variance of the index of relative abundance that we used as the basis of some of these management procedures. We also imposed a random walk to look at non-stationary recruitment deviations, and we looked at time invariant biases in perceived reference points. So we looked at a suite of management procedures, and here it's important to distinguish between model-based management procedures and empirical management procedures. So model-based management procedures use a population dynamics model to get an estimate of stock status. That information is then used to specify management advice. This is akin to sort of the traditional best assessment framework that we're used to. Empirical management procedures, on the other hand, are sometimes called indicator-based management procedures. They take an indicator of abundance, typically an index of abundance, and they use the behavior of that index to adjust management advice. So a simple example is, if an index of abundance goes up, we can assume the biomass of the stock has gone up. We can then increase allowable catch in the next time step. And so we looked at 5 model-based management procedures. They're all statistical catch-at-age variants, where the frequency of assessment varied between 1, 5, and 10 years. And the catch in between the assessments was determined by constant catch, or it was specified using forecast analyses. And importantly, we assumed a 2-year data management lag in the model-based management procedures. We then compared that to a suite of 7 empirical management procedures. These are all sort of baked into the Open MSE framework, so it was easy to use. More information can be found on the DLM tool reference pages, so I won't go into all of them for the sake of time. We did look at the impact of overages versus perfect implementation. I'm only going to be talking about perfect implementation here, and we ran 250 iterations per scenario. So what did we find? This is a results plot for Vermilion snapper. This is showing spawning stock biomass ratio as defined by SSB relative to dynamic SSB 0, plotted over the projection period for the simulation. The horizontal line is sort of a reference line that shows SSB MSY relative to SSB 0. That's calculated at the end of the conditioning period, so this could be changing in the future. But we included it just as a reference line. Each plot shows a different operating model scenario. So the one in the top left is is the base case scenario, and then each different plot shows the different non-stationary scenarios that we looked at. Each line represents the median performance for that management procedure across those 250 iterations. And then all of the lines that are plotted in grayscale are model-based management procedures, and all of the lines plotted in blue scale are empirical management procedures. Phew. So a big takeaway from this is that if we look at some of these regime shift scenarios in particular, we see how some of these empirical, or some of these management procedures more generally, sort of follow those regime shifts, and they can't get back to sort of an ideal spawning stock biomass ratio. But we do see a couple, maybe 3 of these blue empirical management procedures that are a little bit more adaptable, and they can kind of get us back to a more ideal spawning stock biomass ratio. These same management procedures do break down a little bit when the properties of the index changes. This is another way to look at some of these results. When we look at the top right, this is the terminal 10 years of the spawning stock biomass ratio plotted in box plots. And we can see that for the base case scenario, again in the top left, they're not all equal. So it's hard to kind of measure relative performance as these different non-stationary scenarios. So what we did is we plotted the difference values. So we're looking at the difference in terminal spawning stock biomass ratio from each climate change scenario or non-stationary scenario relative to the base case. So a difference value of 0 indicates a management procedure that's really flexible and adaptable and can easily get back to the target sort of spawning stock biomass ratio that we saw in the base case. So a difference value of 0 is pretty good. That's what we're looking for. And we can see again, there are 3 of these boxes that are consistently really close to 0. So that means that some of these blue boxes may be more flexible. Some of these blue empirical management procedures may be a little bit more flexible compared to some of the black boxes. The story is a little bit different with black sea bass. We see even in the face of non-stationarity, all of the management procedures perform fairly well. There's a lot of variability. But looking at the difference values, there's certainly not one management procedure that performs well, better than all the rest. And even in these non-stationary scenarios, the model-based management procedures are still performing very well. So this is maybe a more optimistic scenario for black sea bass. Lastly, red porgy. Remember, this is the overfished stock, so we're starting below an ideal spawning stock biomass ratio. But we do see that in some of these sort of blue highlighted boxes, when there's a regime shift towards lower productivity, a lot of these management procedures are collapsing the stock, but 2 blue lines result in a stock that does not collapse. So maybe these are some good management procedures to look into for red porgy. These are also the same lines that sort of break down when the property of the index changes. So these are the red dashed boxes. And this again is reflected in the difference values. So empirical management procedures are a really great tool. They're really flexible and adaptable. They can be easily modified to reflect a lot of different stakeholder desires. And they're really easily understood by stakeholders. So stakeholders really like empirical management procedures. It's not surprising to find that empirical management procedure performance varies by species, but it's interesting to note that the relative performance of empirical to model-based management procedures also varies by species. These results can sort of be broadly used to sort of colloquially inform empirical or exceptional circumstances. So unsurprising when we have, a big shift in recruitment deviations, if that's not captured in a statistical catch-at-age model, that model probably won't be a good choice to use for specifying management advice. Similarly, when we're following up on empirical management procedures and we're modeling the variability of the indices of abundance that we're using, if the variability or the CVs of those indices are changing pretty drastically over time, we should certainly go back and revisit those management procedures within the MSE framework. But ultimately, empirical management procedures may be better able to adapt to non-stationarity than traditional model-based management procedures for some species. So this certainly isn't to suggest that we throw the baby out with the bathwater. Stock assessments are still very important. We've invested a lot into developing stock assessment models themselves and into the stock assessment enterprise. And they're really, really great at telling us where we are now and what the current stock status of our stocks that we're managing is. But maybe it's not always the best tool to tell us where we're going or how we want to get there. And increasingly, as we're facing non-stationarity and climate change, maybe it's important to kind of broaden the management approaches that we're using to specify management advice, thinking more unconventionally of how to manage through these challenging times. And empirical MPs might be one way that we can sort of broaden the toolbox. So, thank you, and I will answer questions.
Minutes for questions. Saw you first in the back, and then I'll.
Hi, that was a great talk and really interesting. I was curious, and maybe you mentioned it, I missed it, but what either species characteristics or fisheries characteristics influence whether the empirical management procedures perform better for a species versus another, since that did vary between your 3 different species?
That's a great question. I don't have an answer. There are some sort of follow-up exercises that we can do to sort of trade between the biology and the fishing life history, or the fishing history, to kind of see how that impacts our performance. It seems, most MPs perform differently with life history, but it was really interesting to see that the relative performance also varied as well. So I don't have a good answer for you. I'm sorry.
Thanks, Cassidy, for a nice talk. My question is kind of twofold, so I'll try to ask 2 small questions. For your scenarios or your alternative operating models and those assumptions, like different assumptions about M and recruitment, how did you come to develop those scenarios? Like, is that based on empirical studies or something else? And then along with that, are the values that you chose for those like derived from like historical estimates or somewhere else? So hopefully that's not too complicated.
No, it's a good question. So this was all arbitrary. Like I mentioned, we're kind of just imposing these broad changes to measure how the management procedures can perform. They were all relative to sort of current empirical estimates. So when we, looked at high or low age zero natural mortality or recruitment deviations, it was all relative to current. So it was a doubling or a halving. And so it was all kind of relative to the current life history scenarios.
Any more questions? I think we have time for one quick one.
Thanks. So following on to that question, so there's no stock assessment done on these stocks at all?
There is.
There is?
Yes.
But how does that then work when you change the recruitment and the episodic M? Did you look at the hindcast data then in comparison to the stock assessment data?
That's a really great question, and it's one of the really challenging aspects of MSE because everything is automated, and even when we're testing model-based management procedures, we don't totally have the capacity to go back and look at the diagnostics of the model-based management procedures that we're looking at. It's overall sort of a limitation of the approach, and I've thought a lot about that in some past work. And so, yeah, I think it's just a limit of the MSE approach.
Thanks, Cassidy.
Thank you
for your talk. All right. Next up, we have Amanda Hart. And she'll be talking about, her title of her talk is, Does Climate Integrated Stock Assessment Improve Management in American Place Example?
All right, well, good morning. Like Lisa said, my name is Amanda Hart, and I'm a postdoc working with her at the Gulf of Maine Research Institute in Portland, Maine. And I'm posing a pretty big question this morning. Does climate integrated stock assessment improve management? But because this question is so broad, I'm really going to focus on a case study for American Place to give an example of how we've started to go about answering this question for a single species. And on day 4 of this conference, it should come as no surprise that global oceans are warming. And that trend holds up in the Gulf of Maine, where I'm doing most of my work in the northeastern US. In this ecosystem, we've seen the consequences of this warming really impact the distribution of species in the region over time. And these big ecological changes we then have to account for in the way that we're managing our species. At the same time, in the Northeast US, we're shifting how we think about this management approach away from purely focusing on individual species and single species stock assessments and moving towards these more holistic ecosystem approaches to management. So climate integrated stock assessments is one way that we can take what we're doing now and move up this figure on the right to start to incorporate ecosystem and climate context more explicitly into our stock assessments. But this isn't necessarily a new concept, and the benefits of incorporating climate and ecosystem data into management haven't always been realized, particularly in situations where environmental relationships that we felt were very strong have broken down or changed over time. And because of that, there's a lot of opportunity to use tools like management strategy evaluation and simulation testing to really test these methods in advance. So the goals of my project are to understand, do these strong environmental trends that we are already observing in our ecosystems translate into the types of strong stock assessment dynamic impacts that we might account for in our stock assessment models? And if so, how can we leverage this information in these stock assessment models? With the ultimate goal of answering this very big question, do climate integrated stock assessments improve our management outcomes? But back to my case study. There were several reasons we picked American Place as our starting point for this exploration. First of all, there's a single biological stock in the Northeast US, so we didn't have to deal with the complexities of stock structure or interactions with neighboring stocks in Canada. The stock is also doing very well compared to other ground fish in New England. So following periods of really high fishing exploitation, the stock has recovered as we've ramped that fishing exploitation down. And when I started working on this project, American Place was up for a review where we were revisiting the stock assessment methods and also the data that we were using to estimate stock status for the species. And this really left a door open to consider if and how we might include climate and ecosystem context into the stock assessment. But I won't hold you in suspense. The answer to this first question is yes. For American Place, climate is impacting recruitment and distribution of the stock. And to validate this answer, we did a really extensive literature review to figure out what people had done in the past, and then my colleague Jamie Behan led some exploratory modeling to validate that the relationships we were expecting based on the literature were holding up using the data we were going to pull into the assessment model. And for recruitment, this means that we found that American Place recruitment is really closely linked to temperature through broad-scale oceanographic indicators like the Atlantic multi-decadal oscillation or North Atlantic oscillation, but also potentially through surface and bottom temperature. And then we also found that places are shifting their depth and distribution over time in response to temperature. In particular, they move inshore in the spring to spawn in shallower waters, but in the fall season, they're moving into colder and deeper waters over time. And we've seen this play out in our survey observations, where we see these changing distributions of where we observe them over time. So given that we have a yes to the first question, we then have to grapple with how might we use this information in a stock assessment. And to do that, I have been working with the Woods Hole Assessment Model, or WAM, which is an age-structured state space stock assessment model. And one of the great things about this particular model platform is its flexibility. We can use it to generate a status quo approach where we're really not leveraging any of the information I just mentioned. But it also has features to account for time-varying processes by including random effects, including those on stock dynamics like recruitment and survey catchability, for which we have evidence of environmental impacts. And then finally, we can set it up to be a climate-integrated stock assessment model where we're directly fitting two environmental covariates to inform our estimates of processes for these dynamics. And so we can use this model platform to answer or start to answer this third question. And for American Place, really, there's a lot of potential for these climate-integrated assessments to improve management. But there's also a really strong need to improve some of the model diagnostics so that we can verify this before we'd actually make that recommendation to a management body and conduct some further testing. But that said, we found some promising results in that our stock assessment models were returning some of the relationships that we expected based on all of that initial work in exploratory modeling and literature review. So for example, this model fit an environmental relationship to help inform recruitment, and it predicts that under lower sea surface temperature anomalies, our recruitment should get higher. This reflects what we expected in the literature. But it's also not the whole story. As I mentioned, the Gulf of Maine, where the species lives, is warming really rapidly, and at the same time, recruitment has been increasing over time. So while this broader trend of high recruitment under colder temperatures may still hold, it doesn't tell the full story, and it warrants further investigation. Similarly, when we linked survey catchability to an environmental covariate to account for those spatial distributional shifts over time, we found that there was generally a positive relationship estimated by the model. And this means that our model says that fish will, as they move into deeper and colder water over time, it expects our survey catchability to decrease. And this is something that we have actually seen in our survey observations. So that's great. But it's also still a nuanced response. And there were differences in uncertainty as far as the sign and magnitude of this relationship based on some of our modeling decisions in just specifying what type of process was linking survey catchability to the environment. And so again, this indicates that there's hope, there's potential, but there's also a need to really dig into and explore why we might be seeing this and when these models might perform well or where there might still be a lot of uncertainty. And to that end, this is where we're pulling management strategy evaluation into this work. In particular, because it gives us the opportunity to look at what happens when we set up an operating model that has climate-driven dynamics, but then we fit different types of stock assessment model to that data. So we can compare climate-integrated approaches that explicitly use this information to time-varying process models that don't incorporate the mechanisms as explicitly, and compare that to what we're already doing now, which is a status quo, not really considering that data. This gives us an opportunity to explicitly compare one-to-one these different approaches, but also within an MSE framework, because there is this closed loop, we can ask questions about how often do our model diagnostics point us to the correct model, and how variable is that from one assessment to another. A lot of times we don't want those choices to be super variable, and it's important to understand what that might look like. But also, we can, in the operating model, incorporate different information about how strong and what type of environmental effects are occurring for the stock. So whether those are on recruitment or survey catchability, we can look across different emission scenarios to say how strong is it and what are the consequences for the stock. So to wrap up, the approaches that we use to answer our first question and validate when are there strong environmental drivers of stock dynamics, that approach is now being used for other stock assessment processes in the Northeast US. And the Woods Hole assessment model that I've been using in this study has a growing body of applications in management use within this region. And it directly provides a path to consider climate context in management, but the development and testing is ongoing, particularly for these features that integrate climate data. So definitely more to come, but with that, I'd just like to thank my co-authors and my funding sources, and I'll take a question if there's time. Thanks.
Thanks, Amanda. Any questions for Amanda? Not really fair for me to ask you a question, right? There we go. Thanks.
A bit of a question and a comment. Looking at Cassidy's previous presentation as well, when we're looking at the some of the risks associated with some of these empirical models and things under climate change scenarios. So when we're looking at incorporating climate change into these models, are our models, are they sound enough to actually give us good information, I guess, is a question for you as well. And what are the risks associated with it, and how might you mitigate some of those risks in the decision making?
Really great question, and that's why the MSE work is, coming. I will say that one of the benefits of this being a state space model is that we can incorporate time-varying processes without having this explicit mechanism. So we can test explicitly, like, do we think this hypothesis is correct? How does that play out in the context of longer term management performance? But if we don't have that information or there is more uncertainty, we still might be able to incorporate some amount of time varying uncertainty without having quite as strong of a certainty that our individual hypothesis is correct. And so we would hope that that might kind of bridge that gap a bit, while also moving us towards having those more explicit mechanisms in our models when we can validate them. So more to come, but definitely a good question.
Thank you. Any further questions for Amanda? Great. Well, thank you, Amanda.
Thanks.
So thank you. So next up, we have Jan Conradt, who'll be speaking on a climate-proof management of North Sea cod and a deeply uncertain future.
Good morning, everyone. Yes, as was just said, I will present a modeling study on the management of North Sea cod under deep uncertainty and future climate change. Now, the North Sea cod is a major commercial fish species in northern and middle Europe. It is a stock that was quite strongly overfished in the latter half of the 20th century and where catch reductions were taken in hopes to rebuild the stock. And indeed, in the last 2 decades, we have seen some positive developments with spawning biomass increasing again and fishing mortality decreasing. However, as of today, the stock has not yet been fully rebuilt as spawning biomass is still below MSYB trigger and fishing mortality is still mostly above FMSY. In contrast to the positive development in spawning biomass and fishing mortality, the recruitment is actually still on a historically low level. And this, of course, has major implications for the future viability of the stock for its fishery. Now, the fact that the recruitment is on such a low level while spawning biomass is going up may be somewhat surprising, but we have statistical indications that the pre-recruits may be negatively affected by environmental change, and especially climate change, as we see here a negative relationship between recruitment and sea surface temperature. Now, with the stock not yet being fully rebuilt and future warming expected to continue in the future, the future of this stock for its fishery, the future catch potential, is very much in question. Normally, numerical modeling studies like MSE studies could help to explore what levels of catch the stock might be able to sustain in the future under climate warming. However, as with most commercial fish stocks, the severe uncertainty regarding the recruitment process is limiting our ability to make precise projections of stock dynamics under different levels of climate warming and fishing pressure. Now, in our study, we divided the recruitment uncertainty into 3 components. The first component is the uncertainty about the so-called productivity state of the stock. So normally we would assume one continuous relationship between spawning biomass, environmental pressures, and recruitment, represented here by the black curve. However, recent stock assessments have shown indications that the stock may have shifted now to a regime of lower productivity, highlighted by the red curve here, which the stock apparently entered in about 1998. The mechanism behind this shift is not really understood. And so when we want to make future projections, we do not know whether the stock will ever switch back to its original state of productivity or maybe even enter as of yet unknown states of productivity at some point in the future. The second source of uncertainty is uncertainty about the functional shape of the stock recruitment relationship, so whether we have an underlying rigor relationship where recruitment actually goes down at very high levels of spawning biomass, or the saturation-like Bevan-Holt function. The third uncertainty concerns the actual development of future temperature and thus the degree of environmental pressure that the pre-recruits are going to face. This, of course, depends on the climate scenario that will ultimately come to pass in the future. Now, such uncertainties that I just showed are examples of what is so-called deep uncertainties. Deep uncertainties, in comparison to normal or regular uncertainties, are such uncertainties where it is very difficult to make, where it's very difficult to quantify the uncertainty, or if you have discrete future states, it is very difficult or impossible to make probabilistic estimates of the plausibility of occurrence of these scenarios. Now, such deep uncertainties are actually quite common in research on future climate change. For example, this is also an issue in the water management in the Netherlands. And there's actually a science or research branch called Decision Making Under Deep Uncertainty, or DMDU, which addresses future management under such deep uncertain factors. The overall goal of, or the overall paradigm of DMDU is to shift the focus from trying to improve predictive capability of models to actually making good management decisions under the predictive capability of models that we have today. And one prime technique of DMDU is called robust decision making, or RDM. This is actually a collection of visualization and machine learning techniques for exploratory modeling. And the prime goal of RDM, or robust decision making, is to detect policies that perform acceptably successful under a very large range of possible future scenarios. This is instead of the usual paradigm to optimize or to find an optimal policy under a pretty narrow range of assumptions about future development or about system dynamics. We incorporated RDM into our modeling approach, which centers around an age-based population model, which is basically the assessment model of this stock, and incorporates a stock recruitment relationship that is forced by climate data. So when we project, we force this model with projected sea surface temperature from an Earth system model. And the population model is also coupled to an economic model which predicts future profits from the stock. Now, we force this model with different levels of catch in order to test what levels the stock could sustain into the far future under warming. And of course, we also incorporate the uncertainties. So first, the uncertainty about the productivity state of the stock, which we represented by reparameterizing the stock recruitment function by drawing samples from the standard error range of the statistical fit of the stock recruitment model. Then we addressed the uncertainty about the functional form of the SR relationship by running the model both with the Ricker and Van Holt stock recruitment model. And uncertainty about the future climate scenario was addressed by running the model under both RCP 4.5 and RCP 8.5 scenarios. So we ended up with a huge number of model runs where we combined different policies with different uncertain states, and we then aggregated the results and evaluated them in terms of biomass and fishing mortality. So we compared SSB against MSYB trigger and fishing mortality against FMSY. We then used a suite of visualization and machine learning techniques to explore the performance of our different policies. In the first step, we conducted a so-called feature scoring analysis where we used boosted regression tree to find the primary drivers of our model outcomes in terms of sustainability. Here we found that both our policies, or our levels of catch tested, and the uncertainty about the productivity state of the stock, represented by the three stock recruitment parameters, had a major impact on the future sustainability of the stock as predicted by the model. In contrast to that, the choice of the functional shape of the stock recruitment relationship and the climate scenario were of minor importance for model outcomes. In a second step, called scenario discovery, we wanted to explore the properties of fully sustainable model runs. Fully sustainable in this regard means runs where in every future projected year, spawning biomass was above MSYB trigger and fishing mortality was below FMSY. They are highlighted here by the bright yellow tiles. And we found that they only occur at levels of approximately 50 kilotons of catch and below. However, we also found that such successful runs in this range of catch, there are not only such fully sustainable runs, there are also quite a few runs that are much less sustainable, indicated by the purple to yellowish tiles. And this means that due to the uncertainties that we considered, we were actually unable to find a management policy that performed or that resulted in sustainable management, considering all possible future scenarios. In order to still evaluate our policies in some way, we conducted a risk analysis, where for each policy, we counted the number of uncertain scenarios where sustainability was not achieved and divided this by the total number of uncertain scenarios. In addition to the sustainability risk, we also calculated a so-called profitability risk, where we simply compared projected profit against the average profit of the last 2 decades, which is on a fairly stable level. Here we can see the relationship between sustainability risk and the level of catch, and we see a more or less linear increase of risk with catch. We also see a baseline level of about 25% of risk of unsustainable management, even at marginal levels of catch. And in this plot, we see the relationship between profitability risk on the y-axis, sustainability risk on the primary x-axis, and the level of catch in the inserted x-axis. We see a negative relationship between the 2 risk types up to a level of approximately 60 kilotons of catch. And this is, of course, because with higher catches, the chances for good profit rise, but the risk of spawning biomass dropping below the trigger also increases. Above 60 kilotons of catch, we actually have a positive relationship between the 2 risk types. And this is because at these levels of catch, the number of scenarios where the stock actually collapses in the model and no catch can actually be taken anymore increases quite strongly. So here, these levels of catch at some point in time, we actually can't, we can neither make a profit nor can we have a sustainable level of spawning biomass, and thus the relationship is positive. So to sum it all up, we have found that the uncertainties about productivity state of the stock are equally important as our management policies on future sustainability of the North Sea cod. Second, we were unable to determine a policy that works in terms of sustainability under all future scenarios, and this is the reason why we conducted our risk assessment. And third, we found a trade-off between sustainable and profitable catch, at least up to this level of 60 kilotons. With that, I would like to thank you very much, and I'm happy to answer any questions you may have.
Thanks for that talk, Jan. Questions?
Hi, thank you very much for your talk and your analysis. Mark Dickey-Collis, Chair of the IC's Advisory Committee. Much of the analysis, and I think some of the underlying assumptions, are almost implying that it's still a targeted fishery. We are increasingly dealing with a cod fishery, which is in a mixed fishery in the European context, or technical interaction kind of fishery in a sort of a more global way. How does that, or could that affect some of those assumptions, particularly your profit and sustainability risk assessments?
Yeah, thanks very much for the question. Indeed, our model is very simplified in that regard, as we have a single species model here. And it is now more like a guesswork from my side. I do believe that when considering the fact that it is indeed a multi-species fishery, that it does add a new level of basically uncertainty and complexity to the decision-making process in management for this stock. I do believe that when you consider the multiple stocks, there will probably, or you could probably even have higher baseline risks, at least if these other species like haddock show a similar relation or negative relationship to temperature as the cod. And you will probably also have higher economic risks, at least on the single species level, and in particular if the species do not react similarly to temperature. So I do think this would add another layer of complexity and uncertainty. And in our study, we simply wanted to make a first demonstration of this decision-making in a deep uncertainty methodology, but it would certainly be a valuable step to explore multi-species aspects also.
Great. Any other questions? I had one question for you, Jan. On the profitability risk metric.
Yes.
How do you define that? Is that a catch-based metric or yield-based metric only, or is there more like a fleet behavior and structure underlying? How do you characterize profitability?
It is actually it is a pretty simple approach. So we have a simple economic model that translates our realized catches into profits. But that does not consider different fleets. It is simply the total profit made from the North Sea cod fishery. And the risk is calculated by basically comparing the projected profit against the average profit calculated with the same model as the hindcast of the last 2 decades. This is basically a surrogate metric because there's not really a defined economic reference point to evaluate profit as far as I'm aware.
Mm-hmm. Thank you. Any other questions before we wrap up for lunch? Oh.
Thanks. I just thought of one. Well, that last question was asked. Thanks for the great talk. As I understood it, you ran these projections with fixed Fs, right?
No, actually with fixed levels of catch.
Oh, fixed levels of catch. So most management procedures and have a harvest control rule that scales F with biomass. And I'm curious how the more realism of that would impact your sustainability, profitability trade-off, if you have any inclination, or is that like a next step for your analysis?
I'm not sure I understood right. So you were asking how it would perform if we run the model with fixed levels of fishing mortality instead of catch?
Like a harvest control rule.
Yeah.
So there's like the target fishing mortality, but below a certain threshold, then it scales, and then there's eventual cutoff.
Well, yes, that's an aspect that I did not show in this study, and we ran this model also with fixed levels of harvest rate, and indeed in that case we were actually able to achieve a kind of better relationship between profitability risk and sustainability risk, especially where the profitability risk did not increase again, and where we ultimately also achieved somewhat lower risks in total. That's a good point, and that is something that we also consider in this work.
Great. Well, thank you very much for a nice talk and a nice session of talk. So thank you to all the speakers. We'll be back here at 1:30. And thanks to everyone for your attendance.
Hello, everybody. Thank you for coming back again to our session. And now we will start with Allan Hicks, who will talk about management procedures for the Pacific halibut. Welcome.
All right. Well, thank you, Sonia, for the introduction, and good to see everybody back from lunch. Thanks for attending this afternoon. I was going for the longest title. I don't know if I've got it or not, and that might take up all my time if I read it. But I wanted to acknowledge my co-authors, Ian Stewart, Dave Wilson at IPHC, and Piera Carpi, who's now here in Bergen at IMR. So Pacific halibut range over a large proportion of the Northeast Pacific Ocean. They live a long time, they grow very large, and have been observed to migrate very long distances. And a lot of different processes about Pacific halibut are quite variable. We'll talk about this in a moment, including weighted age across years. The International Pacific Halibut Commission was formed in 1923 by a treaty between Canada and the U.S., and it was actually the first international fisheries treaty. So we're 100 years old now. And the Pacific halibut's managed as a coastwide stock ranging from California up through British Columbia and all the way out to the Aleutian Islands in Alaska and up into the Bering Sea to the edge of the exclusive economic zone off of Alaska there. We have identified 4 biological regions for Pacific halibut, and these regions were based on different observations we have, including tag data. And we are still understanding more of the dynamics within each of these regions, but they are interconnected. But we feel that these regions are important for conservation. In other words, maintaining some level of spawning biomass in each of these regions, because we don't know how each region individually connects to the future of the population. So at the Pacific Halibut Commission, we are currently operating under interim harvest strategy policy. And this is the strategy policy is basically broken into 2 parts. One we call the coastwide scale on the left box there, and the other one's the TCY distribution, where TCY is basically the limit, the fishing limit. But the important part here is that there's a coastwide assessment that's done, and a target fishing intensity is used, or a reference fishing intensity is used to determine a fishery limit, a coastwide fishery limit, that's the TCY. But then that fishery limit has to be distributed to 8 different IPHC regulatory areas throughout that entire range of our convention area, as I showed earlier. The key here is that the coastwide scale is based on an SPR-based reference point, where SPR is a measure of fishing intensity. And then the distribution procedure is mostly based on the distribution of the stock estimated from our annual survey. And I say mostly because there is a little bit higher relative harvest rates in region 2 and 3 compared to 4. I note too, at the end of this is a little unusual in the MSE context, is to develop a management procedure that's put into place and then acted on every year. We still have a decision-making step at the end of all of this, and the commissioners may deviate from the management procedure, so that's something we've implemented into our process as well. We've developed a MSE framework at IPHC, which involves stakeholders and managers. It goes from ranging from defining objectives, management procedures, and of course the fun stuff for me is the simulation. And then hopefully that application comes in, and we've had a few successes along the way already. But focusing in on the simulation part of it all, I've seen this figure 4 times today, or this is the 4th time I've seen this similar figure today, and I'm still counting. I'll let everybody know at the end of the day how many times it pops up. And it's interesting to see how people draw it differently, but it's all the same. We have our operating model, and at IPHC, we've developed an operating model written in C++. We had a few things we wanted to implement that were specific to Pacific halibut, but it's very generalized. It operates through input files, JSON input files, so a user can use it without knowing C++, and you're able to link processes to various environmental variables in this. On the other hand, the management procedure, which is linked to that operating model, is written in R. So it's very generalized in that sense, is anyone can come along, write their own management procedure from how the data are collected and analyzed, what the monitoring looks like, what the estimation model looks like, and then what that harvest rule looks like as well. So it's very generalized, and anybody can come in if they know R and immediately implement their own management procedure. So we've been using this at IPHC for the last few years. So looking a little bit deeper into Pacific halibut and how their variability and some of their life history traits, let's first look at weighted age. And here I have a plot of average weight on the y-axis at various age classes, and then the last or almost 100 years on the x-axis there, and the different colors are different ages. So this is the average weight of that age in that year. And what you can see, if you look at that top red line, that's for age 16 halibut. In recent years, an age 16 halibut's on average about 10 kilos. But in the late 1970s, that same age halibut was about 30 kilos. So that's a huge difference, has a really big effect on the biomass of the population. And we haven't found real clear links with the environment or density dependence or fishing that's causing this. So we're still working on it, but every time a study is done, somebody says, I found something, and then the next one says they didn't. We all know that. Looking at recruitment is quite variable for Pacific halibut, but we have linked average recruitment to the PDO, or the Pacific Decadal Oscillation. And we've defined this as regimes, not the specific values in every year of the PDO, but we defined it as regimes of high or low PDO periods. And so you can see in this 120 years, a little over 120 years in this plot here, there's about 5 or 6 different high or low regimes from that PDO. So we've linked average recruitment to that, and that's very interesting on its own, and that's actually implemented in the stock assessment. But we've also linked the distribution of recruits. The operating model has a coast-wide spawning biomass that produces a coast-wide recruitment event, and those age 0 fish are then distributed to each of these different 4 regions, which is also linked to the PDO, so it differs by the PDO regime. Looking at movement of Pacific halibut, that is quite variable as well, and it's a general ontogenetic movement from that region 4 through down to region 2. And you can see on this chord diagram, in green is region 4, and blue is region 3, and red is region 2. And you have some big arrows here that just show amount of movement, basically, moving from region 4 to 3 and then on to 2. And the movement rates in the operating model also differ by PDO regime. So we have that modeled. We have a number of things linked to this PDO regime. And I wanted to point out as well that there's a lot of movement within a region. There's actually a lot of intra-annual movement. So halibut move from feeding to spawning grounds. But within a year, they typically stay within a region, and then across years, they'll generally ontogenetically move downwards through regions 4, 3, and 2. Okay, that's a little background on Pacific halibut, but we've seen some changes in the distribution of halibut over time as well. These are observations from our survey, and what you can see is that there's been a higher percentage of stock biomass in region 4 and region 2 in recent years, and then declines in region 3 and region 4B. So we've been asking 2 questions. One is the IPHC interim harvest policy robust to environmental regimes? And 2, how do fishing and environment affect the distribution of Pacific halibut spawning biomass? So the first way we investigated this was with the MSE model, or this closed-loop simulation, looking at MSY-based reference points. And on the left, we have 2 different models for structural uncertainty, and we have B0 on the top and MSY on the bottom. And those are calculated for the 2 different regimes, a low regime in blue and a high regime in red. And basically what you can see there, this is almost 100 years simulated into the future, so it's sort of a long-term performance metric. But what you can see is that there's a big difference between the low and the high regimes. On the right, when you take a reference point relative to the unfished biomass in each of those regimes, or a dynamic reference point, you can see that it's much more stable. So we have the relative spawning biomass on the top, and then the SPR for MSY on the bottom. And you can see that no matter what the regime is, those 2 reference points are very similar. So the output here is that dynamic reference points provide stable relative management quantities. We looked at it in a slightly different way by simulating the actual harvest policy or harvest strategy and looked at status and yield. In this one, we have relative spawning biomass, the fishery limit, and the variability in that fishery limit, the interannual variability. And we simulate it where both is a modeled cyclical PDO in the forward simulations, and then low is a persistent low PDO, and high is a persistent high PDO. And what you can see, as on the previous slide, is that relative spawning biomass was consistent across both of those environmental regimes. And the fishery limit was what varied quite a bit between the 2 regimes, and then the variability in that limit is slightly affected. So it basically agrees with those previous results. And then finally, we wanted to look at the spawning biomass distribution and how fishing might affect that distribution of spawning biomass, and also how the environment affects that distribution of spawning biomass. So we have the 4 different regions as the different plots, And then we have modeled PDO into the future, that cyclical modeling called both. And we have that now for unfished. So no fishing, and we just simulate it into the future. And what is sort of that equilibrium distribution of spawning biomass? And so in each plot's the percentage of spawning biomass, and then we have it for when fished under the interim harvest policy. We have it for the two environmental regimes as well. And what you can see is in Region 2, we show a little bit of effect from fishing and some effect from the environment. In Region 3, not a lot of effect from fishing, but a lot of effect from the environment. Region 4 is a lot of effect from fishing and barely any effect from the environment. And then 4B is sort of a mixed bag. So really what we found is that it's all over the place depending on where the halibut are. And this makes sense with ontogenetic movement and everything else and relative harvest rates being different down in Region 2. So this is something we're still working on and we're contemplating in the management of this stock. So in summary, Pacific halibut are generally responsive to environmental conditions. They're opportunistic and they can handle a lot of temperatures, so we haven't seen any real shifts in them, but we see them change their behavior depending on the environment. And we're doing a lot of research right now to investigate those relationships. We developed the MSE framework at IPHC, and the harvest strategy is generally responsive to changes in the distribution of Pacific halibut and is also seems to be robust to at least relative to the conservation objectives we have. So before I go for questions, I just want to give a little bit of a plug for some birthday parties we're having at some upcoming meetings, and we invite you to come celebrate with us. We'll have special sessions at the Pisces annual meeting, which is in Seattle, in October this year, and then also at the World Fisheries Congress in Seattle in March of 2024. Thank you very much, and I can take questions.
Thank you, Allan. We have time, but just for a very short question. I'm sorry about, but yes.
I can try. Thank you, and thank you for a really interesting talk. I was just a bit surprised. So basically, and I think you have to walk me through this a little bit, but basically, even though the fish size was much bigger in the 80s, and now their biomass is much smaller, it didn't seem to correlate to the amount of recruiting that goes on. Have you any ideas, and can you put that into your model to understand, or have you got physiologists looking at how I mean, this could be potentially quite a car crash at some point.
Yeah, we're very interested in that question, and as you said, it's confusing when you see that, and there's been a ton of work on it. There was a paper by Bill Clark and Stephen Hare 20 or so years ago that said, oh, it's density dependent, and then future work says, no, it's not density dependent. And we're doing a lot of research. We've started actually we have a great physiologist researcher at IPHC now, Josep Planas, who's been doing some genetic work, has been doing experimentation with growth, and so we're just trying to sort out all that research now and try to understand this a little bit better. But I really can't answer that question definitively right now, except we're hoping to understand it more in the future. Thank you.
Thank you very much. And now it's time for Lisa Kerr. She will talk us about New England groundfish and how ignoring that climate change affects its assessment and management. Thank you.
Thank you. So although I'm speaking today, I'm here really representing my co-author, Mackenzie Mazur's work, who led this as her postdoc, and she's currently at Fisheries and Oceans Canada. So I work in the Northeast US, and we'll be drawing on some work done in the Gulf of Maine, where we've seen relatively rapid warming over the past few decades, and a particularly anomalous rate of warming in our last decade. Similarly, over recent decades, we see some changes and gradual declines in our aggregate fish productivity indices in the region, with our last decade being generally below average. We're also seeing impacts on some of our iconic species in the region, like cod, where we're seeing evidence of increased natural mortality and decreased productivity of cod. This figure shows you, a gradual decrease in the recruits per spawner with increasing bottom temperature anomalies in the region. So we know that climate change is challenging our fishery management system, and we're struggling to sort of keep up with climate impacts. And this is a simplified view of our US fishery management system, where we generally have fish and fishery data that flows into our stock assessment, informs our catch advice, which we then allocate to the fishery and who harvests it back on the resource. And the challenge is, although we're collecting climate and ecosystem information, as well as social and economic data, this data is not really well integrated within the fishery management decision-making loop. So we, in one of the particular issues we're challenged with in New England is a stock assessment issue known as retrospective patterns. We have a large amount of stocks with very large retrospective patterns, which essentially means as you add another piece of data, you realize your contemporary estimates from your assessment are inconsistent. And so here's a little illustration. We often characterize these as retrospective peels, where you sequentially remove a year data. So if you look at your red line, your 2019 assessment, you thought biomass was around 10,000 metric tons, but if you look at the most recent assessment, it tells you it was more like, that perception is more like 5,000 metric tons. So you can see these very large differences in the perception of the stock. And retrospective patterns generally are, in our neck of the woods, a very large source of uncertainty we're dealing with, and they pose really great risks and challenges to setting appropriate levels of catch advice. We've looked at these patterns in stock assessments as perhaps a symptom of unaccounted for climate change. So we reconstructed Mohn's Road time series as how we quantify retrospective patterns for Georges Bank and Gulf of Maine groundfish stocks, and found there to be some synchrony, suggesting to us there might be large-scale drivers of the stock assessment issues. And then we went on to test for some associations with these patterns with some of the prominent hypotheses about what's driving retrospective patterns in the region, changes in survey catchability, various changes in drivers of mortality, whether it be fishing or natural mortality, and found some associations with bottom temperature as well as predator biomass for Gulf of Maine stocks, and associations with these patterns and the proliferation of warm core rings in Georges Bank region. So we were interested in kind of testing our status quo management for groundfish species in our region, which doesn't currently include climate, isn't currently very climate informed, and seeing how it's performing and addressing this question: what are the consequences of ignoring climate impacts on groundfish assessments? So we did this using a management strategy evaluation framework. We have downscaled global climate projections forcing some aspects of groundfish dynamics. Mackenzie's work focused on cod and haddock, but I'm going to focus really on cod results today for time. And so we have age-structured operating models that we generate data that's the same characteristics and quantities that we have in real life. We use the same stock assessment procedure that we use in our groundfish management in the region, the same approach to setting biological reference points, and emulate the harvest control rules we currently use in our process. And then the fishery, of course, implements this back on the resource. We close the loop and simulate. So a bit more detail, we have operating models for Gulf of Maine cod that are age-structured. We have recruitment being influenced by spawning stock biomass and downscaled climate projections. We have an increasing natural mortality scenario that increases from 0.2 to 0.4 over time. In our region, this is called this M ramp, which is considered a plausible scenario for natural mortality changes of cod. And what we're doing with the assessment model is we have an assessment that knows what's happening about climate change, correctly specified, and then we have misspecified assessments that have these incorrect assumptions, so they aren't aware. And we're also testing the performance of some alternative harvest control rules in this context. So this ramped harvest control rule is designed to emulate our current process for determining our acceptable biological catch for groundfish. But we also have this step version of it where we actually just simply shift down when we're in a rebuilding period to a slightly lower, from 75% FMSY to 70% FMSY. And then in our region, there's a lot of interest in stability, so we also ran a ramped harvest control with a constraint that allowed you, or constrained how much you could change catch year to year. So the next few slides, I'm going to show you results. And so just to orient you, what is marked as none is our correctly specified model. Intermediate, I forgot to mention, we had 2 levels of misspecification for natural mortality. The intermediate was assuming, the assessment assumes natural mortality is 0.3, and high as the assessment assumes natural mortality is stationary at 0.2. So 2 versions there. And so what you're seeing here is the true stock performance or operating model output. And so on correctly specified models, so we know we're capturing climate impacts in this model, we can see that all the harvest control rules, the ramp, the F-step and constraint ramp, kind of increase biomass, and it generally levels off. And they work kind of at the same magnitude and timing. As we move across to our misspecified models, this section, if you draw your eye across catch, you can see the misspecified models allow us to kind of crank up the catch, and as a result, you can see lower realized spawning stock biomass over time in these simulations. And we see that things kind of look a little different across the performance of harvest control rules, particularly in this blue one, that constrained ramp. For fish that's, so cod is starting out from an overfish level, it's really, lagging how much we can increase catch over time. So that's why you see that. Here is some figures describing stock assessment performance. On the top, you have the relative error between your stock assessment and your operating model. In the bottom, you have the retrospective patterns from the assessment model. So if you draw your eye up between these two, our correctly specified model, really no error, no Mons-Rowe patterns as you would expect. And as you move towards intermediate and high misspecification, you can see that we are overestimating SSB and underestimating F, and we have positive inconsistencies in the assessment and negative for SSB and negative inconsistencies for F. So we have this overestimation of SSB, underestimation of F, and what was interesting with the retrospective patterns is that actually we were able to elicit retros of the same magnitude and direction that we actually see in our groundfish stocks. We're also interested in management performance. We're comparing our estimated to true reference points, so how well are we doing with the assessment. When you're at 1, that means you're right on the nose, so our correctly specified models, which are shown here across different time steps, do really well. But as you increasingly misspecify or not capturing climate, you're underestimating your SSB MSY reference point. So misspecified models here are underestimating the reference point. And that fact, combined with our overestimation of SSB, can lead to really inappropriate catch advice. So you're kind of in a harvest control rule, you can imagine you're sliding over how long you can stay at high fishing. You're kind of allowing yourself to stay at high fishing mortality for longer than you should. And these are some Kobe plots that describe management performance as well. The way you read these is you don't want to be here, you want to be closer to the green. So our correctly specified models, cod moves from overfished and overfishing. It rebuilds, it actually gets above overfished, which is this dash line, but then kind of lingers slightly below that. And just that reflects those, that even in a correctly specified model, we have this projection of decreasing recruitment over time due to the global climate projections. That means we can't fully rebuild to the target, even with correct, perfect knowledge. Our misspecified models, you're spending a lot more time in the red, so more time overfished, more time overfishing. Trade-offs, we can see, to read these spider plots, you kind of want to be near the edges as much as possible, more area better, more area covered better. So in the long-term view of this, under correctly specified models, you kind of get the best case scenario of these runs. more area covered. And you can see as you move down to the misspecified models, you're really trading off your short-term catch. You're getting more here, but losing on SSB, and you're ending up with higher frequency of being overfished. So in conclusion, so the failure to account for climate impacts on stock dynamics led to this inaccurate assessment, which has this downstream consequences of inappropriate management. Rebuilding to our desired stock thresholds for cod are just not going to happen if we continue to have these large retrospective patterns. And I think this really, highlighted to us that we really need to be focusing on correctly specified models, and that given how large the error is in the assessment, no amount of changes in harvest control rules can perhaps compensate for that because we're dealing with so much error on the assessment side. Mackenzie has a paper, and check it out. She has a great, some GitHub documentation as well. This work was done under this banner of the Northeast US Climate Integrated Modeling Initiative. And I just want to acknowledge our funding source, NOAA's Climate Fisheries Adaptation Program. We also did a lot of engagement, which I didn't have time to talk about today, but those are all the folks who provided feedback on this. Thank you. I'm happy to take questions.
So, is there any question?
Thanks, great talk. My question is about just how sure you are about the signals driving the climate pieces of your operating model. So I'm just curious, like, if that part shifted, would your results here be robust to that? Or I'm sure you guys have thought about it. I'm just curious to hear more.
Yeah, I mean, we have done, this was one version of the operating model. We have done some other versions, assuming, different natural levels of natural mortality. But yeah, certainly, I think we're sort of trying to inform that with our best understanding. I think we feel pretty good. There's been a significant amount of work done on cod to know that there is decreased productivity. We see no signs of that changing, and I think it's been linked to temperature now in a few different studies, as well as natural mortality. I think that one, the exact trajectory of that, we're kind of doing some work right now to re-estimate natural mortality for cod stocks using some life history-based approaches. That's always really hard to feel like you have natural mortality right. It's really hard to estimate. So there's definitely room for more versions of the truth always in these sims.
Any other question? Quick one? Okay, then we will continue because it's true. So, next talk is by Jeewantha, sorry if I don't pronounce your name correctly, who will present us the inclusion of dynamic rates model for adaptive management. Thank you.
My name is Jeewantha Bandara. I'm a second-year PhD student at Rutgers University, supervised by Malin Pinsky and John Wiedemann. Today, I'm going to be talking about our attempts at incorporating a dynamic range model for better and adaptive management of a fish species that's undergoing rapid range shifts. So as you know, the undergoing global climate change phenomenon has had considerable impacts on natural resources, including fisheries. So over the past 40 years, there has been considerable loss of fisheries productivity on a global scale. And warming oceans can impact the range of life processes, including natural mortality, recruitment, and so on, especially for marine animals. And it has been observed that many marine species are moving to cooler and deeper latitudes, which is complicating fisheries management and productivity for many nations, especially on a management side. So our species of interest, the black sea bass, it's an important fish species that's found across the United States East Coast. It's managed as two separate stocks. Today we will be focusing on the northeastern or mid-Atlantic stock. which is just north of Cape Hatteras up to the border of the Gulf of Maine. So this is a very interesting fish. It supports both commercial and recreational fisheries, and as you can see, over the past 40 years, this has been rapidly expanding its range into the Gulf of Maine. As you can see, in 1972 it was around here, now right up to here. So the rapid rate at which this species is moving has led it to being a so-called winner of climate change. So the current stock assessment for the Mid-Atlantic stock of black sea bass, which came out in 2019, concludes that the species is doing exceptionally well. It's not overfished or undergoing overfishing. Its biomass is doing exceptionally well. The current estimated population size is the highest it's been since the inception of the stock assessment. And this has been helped by very favorable, if odd, recruitment years in 2012 and 2016. These spikes is what really interests us when studying the species about, like, you see very sort of stable and normal recruitment years leading up, and then suddenly you get these. And the question is, will these be more common going forwards as it's moving into this novel habitat in the Gulf of Maine? So there has been some interesting questions, especially on the fisheries side, especially as to how are we going to manage this species that's doing so well and is novel to the Gulf of Maine. So the stock assessment considers the largest stock to be divided into 2 subunits, divided by the Hudson Canyon, shown by this brown line shown here, and because, as for many species, it acts as this biological barrier to the species as well. And when we look at the 2 subunits separately, we can see that the larger recruitment spikes are almost entirely by the northern subunit, which is shown in red right here. The southern subunit has more or less held stable recruitment patterns over the last 30 years or so. And so this expansion and this increase in spawning stock biomass and recruitment is entirely by the northern subunit as shown here. So just a plug for our larger working group. The Northeast Climate Integrated Modeling Working Group is basically this collective of scientists from 3 institutions, and our overall goal is to basically develop highly adaptable frameworks for fisheries management and stock assessments in the Northeast that are, resilient to future climate change scenarios. So 6th time maybe today, I don't know. The development of management strategy evaluation frameworks is a large part of this effort. MSEs are basically heavily simulation-heavy frameworks for comparing the performance of different management strategies for different management objectives. So we consider this to be, a superior form of management because there's a heavy reliance on stakeholder participation. And again, well, this is a management strategy evaluation framework as outlined by Punt and colleagues in 2016. But today, my slides will basically go into this part. Basically, we will be focusing on developing a viable process model that can explain the past dynamics of black sea bass and thus can be used to simulate and develop management strategy frameworks for the foreseeable future for this species. So, dynamic range models, DRMs. So this is a subclass of what we would like to call mechanistic or process models. So a mechanistic model in comparison, compared to a correlative model, which are what we normally see in ecological applications, is basically a model that attempts to describe a phenomenon through a hypothesized or assumed mechanism, which is kind of trying to say we try to basically incorporate a fully explained outline into why a certain phenomenon, or in this case, our population dynamics and range of the species might happen. We try to explain it as much as possible, usually in a hierarchical sense. And so the DRM that we wrote for black sea bass is a Bayesian hierarchical model written in Stan, which is a Bayesian language. And we wrote it in RStan, which is this R languages interface to Stan. And this is kind of adapted from a process model or a model similar to this that was written by Alexa Fredston and Dan Obando for the summer flounder. The process model that we wrote is age-based, spatially explicit, which means that it supports different subunits for the species or the population as we see fit. It supports density-dependent recruitment, as well as some forms of dispersal between spatial units, usually age-based dispersal. And it accounts for, obviously, observational and process error as well. So we tried to build in environmental drivers into these mechanistic models as much as possible. So we built in temperature-dependent mortality, temperature-dependent recruitment, and temperature-dependent dispersal, which is kind of not working right now. But that's okay. So this is a basic visualization of our operating model. So as I said before, it's an age-based spatially explicit model. As you can see, the different ages, you can see the density-dependent recruitment, as well as how we have built in this temperature dependence into this process model. And so how do we build temperature dependence, which is one of the interesting questions that we're trying to play around with is, well, it's interesting because rather than just trying to like correlatively model it, we try to basically say, okay, try to develop three competing hypotheses as to how might temperature drive a certain life process, let's say recruitment. Well, we can say that there is no temperature dependence, a first hypothesis, which means that, long increase in temperature, the parameter which drives the recruitment stays stable. And then you have this sort of temperature-dependent Gaussian relationship described by this equation here, which means that there is a certain optimal temperature at which recruitment might be maximized. And then we have a skewed Gaussian relationship between temperature and, let's say, recruitment. And this is a very flexible formulation of a skewed Gaussian, which is basically the same thing as this, but skewed heavily to this or this side, and you can play around with how tall it is. We can take it from here to here, and so it allows us to play around with, different formulations. So the model structure itself, we use Northeast US trawl data and population parameters from the Black Sea Bass stock assessment into this process model. We trained the model using about 30 years of data and tested from the latter 14. Into this dynamic range model. And we specified it to have 8 age classes similar to the stock assessment. We had 7 latitudinal patches, and we set the temperature dependence for recruitment to yes. And it didn't turn out great. So as you can see here, the model, the dynamic range model as it's currently working right now is unable to capture these larger abundances. And I'm still trying to investigate why isn't it doing it as well as we expected. However, you can see that it does well for some patches, but still the inability of the model to capture these larger recruitment. These larger abundances is what's basically what we're trying to investigate right now. So just to see whether the model itself is viable, I basically simplified the model into 2 subunits, north and south, and basically simulated the underlying process model under a range of temperature-dependent scenarios just to see whether, hey, can we even capture some of the past dynamics? And the good news is, so this is the structure of those simulations under a coarser resolution. And the good news is yes, to a certain degree, yes. The northern subunit simulations were able to capture a good chunk of the historical dynamics for spawning stock biomass, shown in red here, as well as for recruitment. It was able to capture the really high recruitment years shown right here. And so for the southern subunit as well, it did well with the spawning stock biomass, not as well with recruitment, even though it got better as we went along. So the good news is that at least the underlying process model can support a specification which comes close to matching the historical dynamics, which is good news. It just seems that we are specifying or misparameterizing the dynamic range model as it is right now. So that gave me a sigh of relief. So at least like the underlying process model is viable, at least for this. So that's what we think. We think that a dynamic range model that factors in these dynamics is vital to the proper and adaptive management of the species. Thank you to the NCLIM working group, the Pinsky lab, the Wiedemann lab, and Fulbright Sri Lanka for giving me the initial scholarship to come to the US. Thank you, and feel free to reach out on any of these avenues. Thank you.
Thank you very much. Any question? Okay, then we will continue as we are just on time. We have now Lauren Rogers accounting for the climate-driven changes in the availability of pollock to assessment surveys in the Gulf of Alaska. Welcome.
Thank you. Yeah, my name is Lauren Rogers, and I'm a fishery scientist at the Alaska Fishery Science Center in Seattle, Washington, part of NOAA Fisheries, and as are all of my co-authors on this work. So today I'll be talking about a case study of one of the ways that climate is challenging our ability to manage and assess fish stocks, and give an example of how we're approaching dealing with that. So a cornerstone of sustainable fisheries management is having good monitoring data. Data from surveys that, when combined with fishery data, can be used to estimate how many fish are out there and what their relative trends are. But we know we're increasingly seeing examples of fish shifting their geographic distributions, their depth distributions, or their migration timing, and all of those are affecting how good our surveys are at being able to capture them, and it potentially biases or introduces error into our stock estimates. So today I'm talking about walleye pollock in the Gulf of Alaska. This is one of our major fisheries in Alaska, and this is arguably one of the best monitored stocks in Alaska and probably in the US. We have 4 different surveys from which we get estimates of abundance or trends from. And when survey trends agree, as shown in this hypothetical example here, we can have high confidence that we're capturing the dynamics of the stock, especially when you have 4 surveys that agree. But when the surveys disagree, or when they start to be really inconsistent with one another, this can lead to increased uncertainty in stock status and makes it really challenging to know, what to do. So this is more or less what happened to pollock in the Gulf of Alaska. So here I'm showing the 3 longest running surveys for pollock in the Gulf. And you can see things more or less agree. For the first part here, there's some decreases and then increases. But starting especially around 2015, 2016, things start to get really weird. And from 2017 to 2019, we had one survey, this winter acoustic survey, that had record high biomass. And we had 2 other surveys which were recording at or near record low biomass. So really conflicting ideas you get of what's going on with the stock from those different surveys. So this discrepancy in these stock trends ultimately, it increased uncertainty in the stock assessment and ultimately contributed to a reduction in the recommended catch limits for the stock as a precautionary measure. So today I'm going to dig a bit deeper into what was going on, potentially with this winter acoustic survey and related to what we're learning about the spawning biology of the stock. So at the same time these diverging trends were happening, it was a really unusual time in the Gulf of Alaska. So starting in 2014, the Gulf of Alaska experienced a record-setting heat wave. It lasted for 3 years, and heat wave conditions returned again in 2019. So it was, there were a lot of really unusual ecosystem observations that were happening during this time. Now, at the same time this heat wave was happening, I was working on a seemingly unrelated project looking at changes in the spawn timing of pollock in the Gulf. And so using using larval data from long-term larval surveys that we've been conducting for over 30 years, we were able to reconstruct the spawn timing, reconstruct the hatch dates, and from there estimate the spawn dates of pollock going back over 30 years. And what we found was that there was, some interannual variation from year to year in the spawn timing. That's shown in these blue dots. That's the mean spawn date. We found that mean spawn timing varied by up to 4 weeks. So there's this period in the late 2000s when spawning was really late, and there was a period, starting here in 2017 is what I've shown, when spawning was actually the earliest we've ever observed within the time frame of this study. So when we dug into this a bit further, we found that the timing of spawning was related to both the stock demographics, so the mean age of the stock, as well as to temperature. And so spawning happens earlier on average when the spawning stock is older and when it's warmer. And so this led us to wonder, could this be affecting the availability of pollock to this winter survey? So the winter survey, this is one of our main surveys for pollock, and it's a pre-spawner survey. So the idea is that pollock are aggregating on the spawning grounds in February and March. They spawn sort of late March into April, and then once they spawn, they disperse rapidly from the spawning grounds. And so that can be a convenient time to survey a stock because your fish are aggregated in one place. And so the survey is designed to happen just before the peak of spawning in the end of March. But you can imagine that if spawn timing is changing right after 4 weeks, then a different proportion of the stock may be available to the survey in different years. And so we went back and looked at how the serving timing and the spawn timing have varied over the years. And so here the spawn timing is in red here, and the survey timing is these orange yellowish dashed lines. And you can see in all years the survey precedes spawning, so that's how it's designed to work. That's what it's supposed to do. But the amount by which it precedes it varies a lot. Like here's a period where this is almost a month in between, or more than a month, and here there's a fair amount of overlap in these really recent years. So if we turn that into a time series and just look at it, I'm calling this survey timing mismatch. These recent years we've had about 15 days in between the timing of the survey and when peak spawning was happening. But there was this period back in 2007, 2008 or so when it was about 45 days in there, so a much bigger gap. So as a first pass to look at are changes in spawn timing relative to survey timing affecting availability, to the survey we looked at the stock assessment and we pulled out sort of what the survey biomass estimates are, and those are shown in black, and then what the model expects those biomass estimates to be based on all the other information that goes into the stock assessment model. And you can see there's obviously a big mismatch here. Like the model just can't meet these data, but there's other mismatches as well, or other misfits, I should say. And so we ended up using residuals from this, sort of the magnitude of this misfit, as a sort of first pass indicator of potential changes in availability. We can do that because we have a lot of different surveys for this stock. So if we look at how those residuals compare to that timing mismatch between survey and spawning, we actually get a pretty good relationship. And so this is showing here, this is positive survey residuals. That is, the survey was getting higher biomass estimates than we'd expect when the survey was more closely timed to when spawning was happening. And vice versa, the survey estimates are relatively lower than we'd expect when the survey was happening much earlier than spawning. So this shows us that these estimates of spawn timing that we're getting from this larval survey actually can explain a significant portion of this misfit of the assessment model to the survey data. So brief summary so far, what I've shown you, changes in spawn timing relative to the survey timing appear to affect the availability of pollock to the survey. And these changes in spawn timing are related to both the age structure of the stock, but also to temperature or to climate. And this mechanism explains the survey biomass discrepancies for this period, this recent period, 2017 to 2019, where it was really egregious. But it also explains the residual patterns for prior years when it wasn't so obvious that there was maybe a problem or a process that we needed to account for. And so what this tells me is that This isn't just some weird one-off ecological fluke, but this is something that we actually need to account for in our monitoring and in our management. So then that's the next piece I'm going to talk about, which is how we're now working to incorporate this time series of sort of this mismatch between survey timing and spawn timing directly into the stock assessment as a catchability covariate. There. So for this part, I've been working with Cole Monahan, which has been great. He's our current stock assessment scientist for the walleye pollock stock in the Gulf of Alaska. And the current assessment for pollock is an age structure integrated assessment model. It's coded up in ADMB. And Cole has worked now to port this model over to WAM, which is the state space assessment model framework that you've just heard a great talk about and have been really well introduced to. So we considered 4 different catchability formulations that we wanted to test out. The first was just a constant catchability. The second is a random walk, so that allows catchability to be time varying, but there's no sort of mechanistic basis for it. But it does allow it to vary through time. The third was including this timing covariate directly as a catchability covariate in the model. And the fourth was with a timing covariate and a random walk together. Sort of the most flexible option. And then we compared these models using AIC. We also looked at the magnitude of the random walk process error for the models that had this covariate, this extra timing covariate, and the models that didn't have that covariate in it, and I'll show you that. But first, I'm just going to show you the model fit to survey data. So here's what I've shown you before. This is assuming constant catchability, and we already know that doesn't do a good job of, we have a poor fit to the survey data in that case. So the gray line there is assuming constant catchability. If we then look at a random walk, it actually fits the survey data really well. It's a quite flexible model there, but that comes at the cost of it's a really high process area that's associated with that. It has to estimate a large sigma to be that flexible, and there's no mechanism under there. If we look at just including this timing covariate on its own, it actually does a really good job as well. And that's that explicit what's number of days between the survey and the peak spawning. And then if we look at both of them together, it fits the data even a little bit better. And that's supported if we look at the change in AIC. So, all of these models that have time-varying catchability, they're all better than constant catchability. And I would say the take-home here is that those that have timing, that explicit timing covariate included, do the best. They have the best performance. And if we look at the change in the sigma that's estimated, the error associated with the random walk, and we see that there's a 75% reduction in that random walk process variance when we include the explicit timing covariate in there. So the next step now is moving this from this research track model, which is where it is, into an operational stock assessment. And I'm hopeful that I'll be able to give a talk on that sometime not too long from now, but we'll see. Check back with me next time. But that's sort of the process we're trying to get started now, and it is a process, as everyone knows. So to conclude, we identified a mechanism in this case that's driving changes in the availability of pollock to the survey. And we were only able to do so because we had this great long-term monitoring program going on for larval early life stages, and we were able to learn something about the spawning biology of the stock from that. It was really fortuitous in this case. We couldn't have planned that and gone back afterwards and said, oh, I wish we had this, right? We happen to have it. We found that including the spawn timing, survey timing mismatch as a covariate resolves the historical data conflicts, and it has the potential then to reduce this uncertainty in management advice, which is what we had a few years ago when we were confronted with this situation. Now, what I haven't shown, but I think is really interesting, is that when we looked at models that had temperature alone, that is, they didn't have this, it wasn't the timing mismatch number of days, it's sort of more mechanistically based, but it was just looking at temperature, which we know is a driver of spawn timing, right? Those models were much less supported. It was better than assuming a constant catchability, but it was not nearly as good as when we looked at the sort of actual mismatch that we measured. And what that tells me is that a climate-informed approach, but a climate-informed but mechanistically naive approach is insufficient in this case. Like, it's better than nothing, but it's a lot better if you understand the mechanism, what's going on, and you can actually account for that. So that's my take-home message here, is that we can expect that as climate change accelerates, we're going to see more and more of these cases where changes in the availability of fish stocks to our survey gear are going to be, it's going to be a growing concern. And so I think that this work really shows how important it is that we're tracking and understanding spawning dynamics, migratory behavior, phenology, distribution shifts, things like this, because this knowledge is really going to be key when it comes to climate-ready fisheries management. So with that, I can take any questions. Thanks.
Thank you, Laurie. Is there any question in the room?
Yeah, thanks for the great talk. So I'm wondering, it seems like the mismatch might be kind of parabolic. So if the survey is too early, you might miss them. They're not there yet. And if the survey is too late, you might miss them because they're already gone. Have you considered like a quadratic relationship? Not just a linear one, but a quadratic?
So I think we could consider that, but it isn't supported by the data, first of all. But I think the other thing there is that so far, I think the survey hasn't been too late. So we don't have the data on that to inform that. But it is a risk, right? Like if and that's why I'm not advocating for changing the survey timing, because I think if it is too late, it's sort of an asymmetric risk. So I think it's a better approach. What I'm advocating for is accounting for it sort of after the fact in the assessment in this way as a catchability covariate. Yeah, good point.
Okay, thanks.
So a question on the surveys you use. So you used an acoustic survey. You mentioned trawl surveys, and it looked from one of the plots that the acoustic survey was showing lower biomass. I have two questions. Can you get rid of the trawl surveys and only use acoustics, and you're all good? And did you do it with other surveys to see if you get the same relationship in there?
Well, I mean, this process is really specific to that acoustic survey because it's a winter survey on the spawning grounds. The trawl surveys are summer surveys and sort of dispersed across the Gulf of Alaska. But there are different processes that are affecting availability to those other surveys that are unrelated to the spawn timing in this case. And the question of whether you can get rid of one survey and just leave the other, I will not comment on. Well, I will comment. No, I don't think you can. I think we're learning different things from the different surveys. So, yeah.
Any more questions? Okay, thank you. Sorry.
Just another quickie that it just speaks to the fact that you kind of need, for options and insurance purposes, you need to keep these programs around. The one you called fortuitous, you need these things and you don't know when you're going to need them.
Thank you for that point. Great, thank you.
And our last talk before coffee is from Matthew Robertson on sequentially testing models of increased complexity to develop ecosystem-informed fisheries advice. Thank you for being here.
Thank you. Thanks, everybody. As mentioned, my name is Matt Robertson. I'm a research scientist at the Marine Institute of Memorial University. And today I'm going to be presenting some of the work that I did for the last chapter of my PhD thesis. Before I get started with the presentation, I just want to make sure I take the time to thank and acknowledge all of my different funding agencies and the many different people that were involved in this work. So a lot of this session has focused on the development of tactical ecosystem-informed fisheries management advice. When I'm talking about tactical fisheries management advice, I basically mean the day-to-day processes we use to manage our fisheries, things like setting catch, effort, area, and gear controls. And why we're talking so much about this tactical ecosystem advice is there's been a lot of different papers in recent years that have shown that even though we know the ecosystem is impacting all of these fisheries that we're interested in managing, oftentimes what we're seeing is that management advice really is infrequently including quantitative assessments of ecosystem effects on stock productivity. And one example of this comes from a recent paper by Pierre Pepin and colleagues, where they looked across all stock assessments in Canada and tried to see how frequently we were including even qualitative assessments of the importance of climatological, ecological, or ecosystem or oceanographic effects on these different stocks. And what they found that, again, even qualitatively, we were only doing this in less than 30% of our assessments. And one of the main reasons they said that this was so infrequently occurring and was not effectively occurring was because we didn't have a framework for how we could actually assess which ecosystem processes were most important and which population processes they might be affecting, and how we could use that within our stock assessment process within Canada. And so today's presentation is going to focus on potentially developing a framework that we may be able to use to rectify this problem. And it's going to do this by using a particular case study for some flatfish on the Newfoundland Grand Banks. These two flatfish species are NAFO Division 3LNO American Place and yellowtail flounder, and you can see a time series of what we've estimated their spawning stock biomass to do through time. And what we saw for both of these populations is that, like many of the other populations around the Newfoundland Grand Banks region, they underwent fairly dramatic collapses during the late 1980s to early 1990s. However, after this, we started to see a difference between these two stocks, where soon after the collapse of yellowtail flounder, we saw that they recovered pretty quickly and dramatically to have biomass levels above what we'd seen historically. Meanwhile, American Place has still maintained this collapsed state 30 years later. And these dramatic differences that we see in these recovery trajectories are despite both of these species inhabiting very similar environments, having very similar life history characteristics, and having the exact same fisheries management measures imposed at the time of their collapse, specifically a directed fishing moratorium. We saw that fishing moratorium removed for yellowtail flounder when they recovered, but it still remains in place to this day for American Place. And because of this, we really have this big question of why, despite so many of these similarities, have we seen such a dramatic difference in the recovery of these two different stocks? And so to be able to address this question for these stocks and develop a framework where we may be able to more consistently assess what population and ecosystem processes are most important to include in our stock assessment models, I've created a model comparison framework where we compare models to identify the most likely population and ecosystem processes that affect recovery by sequentially comparing models of increasing complexity. And so you can see a conceptual diagram for this framework shown here, where on the left side of this figure, you can see sort of the most simple are null models, where we assume that all of the dynamics are based on the single species dynamics that are currently assumed within their stock assessments. So that most of the temporal variability that we're seeing in their population is coming from fishing mortality and variability that we see in recruitment. We can then move up to our more sort of intermediate level of complexity that I've considered, where we might expect that recruitment or natural mortality are impacted by an environmental covariate. And then finally, we move up to the most complicated version of the stock assessment models that we consider here, where we might expect that actually these two different species are directly competing with one another, and that this competition is resulting in some sort of effect on their recruitment or natural mortality. And so to be able to do this in practice, I've used a model comparison framework very similar to what we saw in the last talk, actually. The first step of this involves qualitatively comparing the null models that I created for the population dynamics for these two different stocks, and specifically in their SSB estimates to estimates that were coming from the previous stock assessment models. We needed to do this because I was actually using a different stock assessment or population dynamics framework for both of these stocks compared to the current stock assessment framework. So for American Place, I used an age-based state space model, while for yellowtail flounder, I was using a state space delayed difference model, where American Place currently is assessed using a VPA, and yellowtail flounder is assessed using a surplus production model. In both of these population dynamics models that I created, I estimated recruitment and natural mortality using process deviations that followed a random walk. Once I saw that the spawning stock biomass estimates from my new models seemed to be doing relatively similar, or creating relatively similar estimates for spawning stock biomass as prior stock assessments, I then compared these null models to models that then included time and or age varying natural mortality. The prior stock assessment models had not included these estimates, but they had been hypothesized as potential drivers for the differences in the recovery trajectories that we'd seen. So I wanted to see if these were processes that we should be estimating over time for these populations. And I compared these using AIC and model fit diagnostics. I then moved forward to the last step of this model comparison framework, where I used the best model from step 2 to then identify if ecosystem covariates or competition could help us explain some of the temporal variability that we were estimating in recruitment or natural mortality. And so now we can get to the results. And so this slide shows us the best, 3 different population formulations that I examined, and the best one that was identified for both species. So in this figure, you can see for both American plaice and yellowtail flounder, lines for the current assessment shown in gray, our single species model shown in purple, and the single species model that included time-varying estimates of natural mortality shown in orange. You can see for both stocks that there are qualitatively similar trends for both species, but that we do see some dramatic differences in scale depending on the time that we're looking at for a particular stock. For example, for American plaice, you can see that the largest differences we see are in the scale for spawning stock biomass, especially in the middle of the time series, and we expect that this actually has to do with differences in the level of total mortality that's estimated depending on what we assume about natural mortality. And from this process, we identified that the best model for American plaice did actually include time-varying estimates of natural mortality. Can then move on to yellowtail flounder, where we saw that the best model for them actually only included estimating variability in recruitment and not natural mortality. And here, the biggest difference that we see is sort of at the end of the time series, where that point of recovery for yellowtail flounder is estimated to be quite a bit lower than what had been estimated in the prior stock assessment. And this difference seems mainly to be due to differences in how catchability were estimated in the prior surplus production model in comparison to my delay difference formulation. Moving on from this, once we'd identified what processes we need to include for the population to be estimated through time, we then wanted to understand what ecosystem processes needed to be included. We found that including competitive interactions directly between American plaice and yellowtail flounder actually didn't improve our estimates at all. Instead, for both of these species, we saw that something known as the Newfoundland Climate Index, an integrated index of the regional variability that we observe in our climate around the Newfoundland region, helped explain processes for both American plaice and yellowtail flounder. Specifically, we saw that American plaice natural mortality estimates were improved with this Newfoundland Climate Index, where we were estimating that natural mortality increased at colder temperatures. Meanwhile, for yellowtail flounder, we estimated that recruitment was affected by this Newfoundland Climate Index, where we were estimating that recruitment would actually be better in colder years. And this ran a little counter to what we had expected prior to running these analyses, because yellowtail flounder on the Newfoundland Grand Banks are actually at the northernmost extent of their range in the Northwest Atlantic. So we had kind of expected that warmer temperatures would actually be better for recruitment, and our model was telling us something different. And so our expectation here is actually what the model is estimating is likely something that's more ecological rather than physiological, where likely what we're seeing is that colder years delay spring bloom of phytoplankton and zooplankton, which actually better align the availability of those larvae with the timing of the spawning for yellowtail flounder. Now, once we'd run this process to see what processes we needed to estimate and which ecosystem components were most important for estimating that temporal variability, I was interested in understanding whether these estimates that we'd come up with could actually help explain the things that we'd seen historically. And so what I did was ran some simulations with alternative climate histories to see if now those relationships that we'd included within these population dynamics models could help us better understand those differences that we'd seen. And so what we see within this figure are several different panels where each column represents different climatological conditions, warm, average, or cold, where we had random variability around an average climatological condition for each one of those panels. The top row represents the dynamics for yellowtail flounder. The bottom row represents the dynamics for American plaice. The black line shows what we actually estimated population dynamics to do throughout the time period, and the gray and the orange polygons represent the simulations that we had with those alternative climate histories. And what we were able to see from this was that for yellowtail flounder, it likely wouldn't have recovered, at least not as dramatically, if there had been warm conditions following their collapse. Meanwhile, under both average and cold conditions, we saw at least some degree, if not even more recovery than was actually observed. For American plaice, we actually saw essentially the exact opposite, where American plaice would not have collapsed as dramatically if we had had warm conditions following the initial part of their population collapse. Meanwhile, under both average and cold conditions, we would have seen a collapse, but to differing magnitudes. And so with this work, we have a few key takeaways. By sequentially comparing these models of increasing complexity, we were able to identify what we expected to be relevant population and ecosystem processes for these two different species that we're trying to manage on the Newfoundland Grand Banks. Where specifically, we saw that the population dynamics of both species were affected by the same driver, a driver indicative of regional climatic variability. And more generally, we expect and sort of hope that this structured hypothesis testing framework that we've developed here may be able to make a more consistent framework for trying to understand how we can include ecosystem considerations within our stock assessments in the future and how we can quantitatively assess these effects on stock productivity. I thank you for your time, and I'm happy to take any questions.
Questions, please.
Yes, thanks a lot. So I'm not totally sure if I completely understood it, but if you would now have a warming environment, would you actually expect the stock dynamics to reverse so that the one species would take off and the other is going to be going down? So is it also suitable to make, in a way, predictions under changing climate?
That's a really good question. So within both of these populations, I think what we've seen for yellowtail flounder is throughout the entire time period that we estimated, it seemed like temperature was very influential. But the way that we estimated the deviations, the process deviations for recruitment and natural mortality basically made it so if there was a period where the ecosystem covariate isn't explaining those deviations, then they can still follow a random walk. And that's actually what we saw for American place, was that those cold temperatures that affected their natural mortality seemed to be most important during the period of collapse, and there may actually be a different environmental driver for them in recent years where we're seeing the deviations sort of follow an oscillatory pattern. And so it may not actually be that their dynamics are much affected by climate anymore, just because we haven't seen as cold of years as we'd seen during the period of their collapse. So that's something that'll require a little more examination to see what that driver is that's following that sort of oscillating pattern.
Any more questions? No. So thank you very much.
Thank you.
So we now close for the coffee break, and we'll be back in half an hour. Thank you very much.
Welcome back, everyone. I think it's time to get started. Our next talk is going to be Kristin Marshall, who's going to tell us about climate risk planning and decision-making in transboundary fishes. And it looks like she's all mic'd up and ready to go.
Thanks, Cassidy. And I think that I might have had a longer title than Allan, so I might win that one with the colon in the middle. Thanks, everyone, for being here and joining us for this afternoon session. I know we're getting close to the end, so I hope I can keep you entertained with some stories of Pacific hake. And I want to acknowledge my co-authors here on this work, all from the Northwest Fisheries Science Center in Seattle, where I come from. It's a really great collaboration of stock assessment scientists, people working on MSEs, and ecologists and quantitative tool developers. And so this work is really about focusing on this key challenge of trying to match spatiotemporal scale of predictions and models to management needs. And so I think this, the figure from one of Desiree Tomasi's papers from a few years ago highlights or sort of illustrates this challenge. And often, you know, we're thinking about, with our MSE work, maybe something out here in thinking about these long-term predictions or long-term projections, but at the same time we're trying to develop these tools that can be used with our annual catch setting processes. And so how do we identify the tools and models for both the biology and the climate pieces that to come together to actually inform the management process? And so that's the key question of my talk here, is thinking about how to operationalize research on drivers of recruitment for use in fisheries management. And so if you saw Lisa's talk the other day, she used the analogy of on-ramps. I like that one a lot, so I've got some on-ramps here. But I think the story here that we've been experiencing in Pacific hake is, in addition to building these on-ramps, we have to be ready and adaptable to hitting some speed bumps and sometimes some traffic circles where we might go around a couple times before we're actually ready to get onto the freeway. So these are going to be the things that I'm going to be talking about. And so I work primarily with Pacific hake, which is a dynamic and transboundary stock. It's managed under an international treaty between the US and Canada, and it's has really variable migration and recruitment, and with indications of links to ocean conditions that have been investigated in the literature, but not yet brought into the production management process. And so here I'm just showing you, for example, the stock recruitment relationship for Pacific hake, and what you can see is that there are a lot of really big and really small recruitment events that are happening across a range of stock sizes. And so this is a particular challenge for trying to identify recruitment drivers and sort of try to reduce that variability. And so one way to look at this is through an MSE. So here's my MSE loop diagram. I have circle boxes instead of square boxes, but otherwise it's the same. And so we've been developing a management strategy evaluation for hake for the last couple of years, where our goal has been to evaluate the performance of the current and alternative hake management procedures under current and future environmental variability and long-term change. And so I guess the key highlights that I will point you to on this slide is in our operating model, we have a spatially explicit operating model with two boxes that we move the fish between the US and Canada. They move north to the north during the summer to have good productive feeding grounds, and south to spawn in the winter. And we're interested in looking at a number of different uncertainty scenarios around the demographic processes for hake, so migration, growth, and recruitment. And so we had a postdoc that we were working with for a few years, Nis Jacobson, who published, he sort of developed the simulation framework for the MSE and published this paper that came out in ICES last year looking at some climate change-induced movement scenarios for the hake stock. And so he looked at a couple of different harvest control rules that kind of capture the way decision-making is happening currently, and looked at then some forced movement scenarios. So these were conceptual scenarios for what happens if you shift the center of the distribution of the stock, or more of the stock, northward in the future. And what he found was that the risk of fisheries closures here is increasing when you start to induce these climate-induced range shifts. So moving, that you start to exceed the manager's risk tolerance for fishery closures. However, so this was a really great finding, but at the same time, a big piece of this work was identifying how important the recruitment variability was in dominating the effects of these distribution shifts. And so that led us to sort of a new line of work to try to more holistically identify the drivers of hake recruitment variability. And so we worked with a postdoc, Kathleen Vestfalls, who has a paper that's coming out, I think, like this week in Fisheries Oceanography, to try to identify what some of these drivers were. And so the method that she used was to develop a conceptual life history model for hake, identifying all of the important stages, and then confront that with our ROMS model that we have for the West Coast to identify potentially important ocean indicators of recruitment. And then do a bunch of model selection to try to figure out which ones mattered. And so her work was able to identify sort of a handful of factors that we think are correlated with hake recruitment. And this was able to explain about 2/3 of the recruitment variability from the stock assessment, the deviations from the stock recruit relationships. And so this was very promising. We were really excited about this, and so then our next step was to sort of take which of these indicators we could from the ROMS model and ask, okay, how can we move these forward into more of a projection sense for the MSE, and how can we think about shorter term predictions for the stock assessment model? And so we thought, okay, this is great. We're all good to go. We're just going to take our ROMS model indicators that we've identified and then sort of go from that to the ROMS projections we have for the West Coast, project recruitment in the management strategy evaluation, and then do our testing of robustness of control rules and thinking about how we would incorporate these in the climate-linked assessments. And at the same time, we were working with the stock assessment scientists to try to operationalize this within the stock assessment framework in the near term to help reduce managers' uncertainty about what's going to happen this year with the Hicks stock. And so quickly, we figured out that this was not going to be as easy as a beautiful conceptual diagram might suggest that it might be. And so there's a number of road bumps and roundabouts that we've hit. And the rest of my talk is going to focus on sort of how we're navigating that. So some of the challenges that we face are differences in spatiotemporal coverage of available ROMS products during the historic period versus the sort of most current period into the future, some low explanatory power of relationships between drivers of recruitment. So if it takes 5 variables to get to 60% of the recruitment variability, sort of how do you move forward with that? And some sort of limitations in the stock assessment model structure and its ability to incorporate multiple covariates. And so we had sort of taken a roundabout here to think about using more of a big data approach to reduce the number of covariates and explore a larger set of models and model structures to explain this recruitment variability. And so here, what I'm showing you, I'm going to explore some non-mechanistic models comparing different model types and both univariate and multivariate responses. And then in addition to thinking about the ROMS-based Hake life, or sort of the Hake life history-informed ROMS variables that came out of Kathleen's work, we're also exploring some products and indicators that sort of allow us to go all the way from the 1950s to present, or the 1980s to present, without having to deal with this a gap that we have in our ROMS products. And so we're looking at some survey time series of larval and juvenile fish abundance and asking whether the sort of combined information from those can help us. So I'm going to show you some results from this model fitting exercise, and here's just one plot from this showing you just the Hake-inspired ROMS variables that we looked at. Previously, we were using linear models only, so the linear model performance, each one of these dots here is going to show you the performance of one set of model covariates, and that you're showing the top 30 best performing models across all of the ones we looked at for each set of covariate, each set of model types and indicators. So you can see here that the GAMs that were in here in green perform a lot better than the linear models. And so this was really helpful for us in thinking about maybe we can do better with fewer covariates using more flexible models. And then when we look across all the different sets of indicators that we explored, we also saw really good performance with the larval surveys. So these are from Cal Coffee. And so this was sort of, at least just thinking about the projection piece of moving forward with this in the MSE, we're able to sort of validate the Hake-specific ROMS indicators against some other potential indicators and think through how these covariates that are supported by mechanistic hypotheses in ROMS are also being comparably are comparable with some of the non-mechanistic selected variables from the larval survey. So this is all well and good, and again, this is in our training period, but what we really often care about and with this kind of work is the out-of-sample prediction. So what's our ability to predict what's going to happen next year? And so with that, we wanted to look at the performance of 1 year ahead forecasts of recruitment using moving window out-of-sample prediction. And here we're measuring performance as a reduction in the error that compared to a null model over 10 1 year ahead forecasts. So now what we have is a similar looking plot looking at the performance of these different surveys and indicators. I'll note though that here is our 0 line, so anything below that is doing worse than a null model. So when we look at the 1 year out performance, what we see is that the Cal-Coffee indicators here are the ones that are doing the best, again using these GAM models. And so this is helpful in that because we don't have our ROMS variables, the Hake-inspired ROMS variables from this most recent period, it looks like we might have a promising source to use in the larval indicator, in the larval data. And this is larvae for not just hake, but other species, and so using multiple species to indicate the ocean conditions that hake are experiencing in their early life stages. And so this seemed really promising as potentially going around our roundabout, maybe we're ready to on-ramp this. However, we have discovered that when we move this forward to the most recent period, including now forecasts up to 2020, our performance just really drops off. And so there isn't very good improvement over the null model in this most recent period, suggesting there's some sensitivity to the assignment of testing and training data. And so I just want to wrap up here by saying, this is very much work in progress, but I think that we've been able to sort of validate the ROMS life history-based approach to variable selection, at least for use in our training period, and we have this to move forward with in our MSE. In the sort of near term, the ecosystem indicators of the larval stages might be useful for these 1 year ahead recruitment forecasts. And I think we've shown here that there's frequent updating might be needed for these kinds of approaches, especially given the non-stationarity that we seem to be seeing. And so the last take home here is really just, I think we should expect speed bumps and roundabouts when we're trying to on-ramp some of these studies. And with that, I'd love to hear your feedback at the break probably and take any questions. Thanks.
We do have time for questions, so do I see any hands? Yeah.
Yeah, thanks for a very good talk. So I'm wondering, in terms of management implications, like how much of next year's catch is, kind of hinging on the forecast recruitment for next year?
Yeah, so the way that the decision process works for hake is, there's the number that comes out of the stock assessment for what the sort of maximum for what could be caught, right? And then there's a negotiation process that happens between the two countries to actually set the TAC, and that always comes in below that. So I think that one of the key potential places for this to be useful is actually in helping the managers in their negotiation process, because there's different levels of risk tolerance among the multiple parties involved. And so having a better sense of what recruitment is looking like this year, or what recruitment is looking like this year makes them more comfortable with setting, higher or lower tax for the following year. So at least that initially, I think, is probably the most likely on ramp for the recruitment forecast, because it's not that they're catching a lot of age zeros. It's that they want to know what's coming so they can feel better about their decisions.
Gotcha. Thanks.
Any more?
Thanks, Kristin. I'm curious if you've looked at, it's a transboundary fishery, and I wonder if the sort of proportion of the population that's sort of like in Canada, if that is something that is sort of predictable, separate from the recruitment stuff, and if that's something that would be, I could imagine, useful for this process as well.
Yeah, great question, Owen. And so far, the conceptual scenarios we did in the MSE just kind of assume that things are going to move north, but it's really variable year to year where the hake stock is. And there is some good work from Mike Malik that has informed our understanding of the role of temperature in that.
However, there's other factors beyond temperature, and we don't know all of them yet. So I don't know that we have a really good predictive model. I mean, we have sort of in-season forecasts that come from the JScope model that sort of show the probability of observing a hake in the two countries, but we don't know how much biomass is going to be in the two countries ahead of time. So, yeah, it's work in progress.
I think we need to move on, so make sure you catch Kristin tomorrow or today if you have another question. And I want to offer a friendly reminder to all of our speakers to keep up with the app, because you might have gotten some questions along the way from those of us who can't be here today. So with that, our next speaker is Grant Adams, who's going to talk about performance of single and multi-species management strategies under climate change. Take it away, Grant.
Awesome. I feel like I'm going to sell you guys a ShamWow with this thing on. Yeah, so I'm going to talk to you all about some of the work I've been doing with multi-species modeling in Alaska. So as many of you all know, the majority of the models that we use to manage fish stocks currently are these single species population dynamics models that relate the dynamics of a single population to the fishery that we're interested in, or fisheries. But in reality, we're working in these multi-species systems where fish eat other fish, and our management decisions for one species can have implications for either predators or prey. And when we know that when not accounting for these predator-prey dynamics, this can lead to a few negative consequences. Specifically, the reference points that we use for management may be biased because we're not accounting for the productivity that is dependent on other species in the system. These models, these single species models, have been shown to have poor at-a-sample predictive performance by some work by Vanessa in 2020. And I think ultimately this leads to suboptimal decision-making. We're either under or over harvesting the population to where we could be. And the majority of studies in the past that have tried to get at kind of multi-species dynamics and management have really been focused on either projection studies, where you take one model and project it under some catch stream from another model or from that same model, or a simulation study where you simulate data from one sort of model and then fit it to another sort of model to evaluate bias in the model quantities that you estimate. And I think largely these sorts of studies don't account for feedback control that we have in our management system. We go out year to year, collect data, update our assessments based off of how the stock or population is trending. Some of these studies types of studies don't account for the dynamic feedback between species. And also they may not necessarily be trying to get at our objectives that we're really interested in, our management objectives. So this work is kind of the first step of what we're trying to get at, of whether or not we need to use multi-species models in fisheries management, and it's trying to get at kind of whether or not single species models are adequate. And we'll be using a single and multi-species model that we've developed in Alaska, and as everyone's heard a lot about, we'll be using MSE approach. The model we're using is Seattle. It was developed by Kirsten Holzman for the Bergen Sea, and I came in and ported it over to TMB and applied it to the Gulf of Alaska. It's named after the city we're located in, and I always mess up pronouncing all those words, but you can read them. And it's essentially a multi-species age-structured model where the numbers of one species at age and year is a function of the numbers of the same species in the previous year and the previous age times some mortality component. That mortality is decomposed into a residual mortality that accounts for death due to disease, predators not accounted for in the model, old age, what have you. And then this M2 term, that is predation mortality from predators that we explicitly include in the model. And then, of course, fishing. So as I mentioned, there's two models that we developed for the Eastern Bering Sea and the Gulf of Alaska. And for this work, we're using both models because the predator-prey dynamics are slightly different between the two systems. There's 3 species in each model: the walleye pollock, Pacific cod, and arrowtooth flounder. And as illustrated by the arrows here, the predator-prey dynamics are slightly different, where in the Bering Sea, you get more cannibalism of pollock, while in the Gulf of Alaska, it's more top-down, where arrowtooth flounder tends to eat cod and pollock, but there's less cannibalism. So going through our MSE approach with circles, not squares, actually ovals, we're using the multi-species models that have that predation mortality as our operating model. And this represents the truth, what's actually happening in the system. We simulate survey and fishery data from those multi-species operating models, and then fit single species estimation models to that simulated survey and fishery data. And then apply some decision rule, harvest control rule, to output a catch that we plug back into the multi-species operating model in the next year. We then continue doing that for multiple years, simulating data, fitting a single species estimation model, applying some decision rule, and plugging it back into the multi-species operating model, and summarize it all up by a few performance metrics that we're interested in relating to our management objectives. And we looked at a few different scenarios in this case. So we have the multi-species operating model, and we have a few different climate scenarios, mostly related to kind of differences in recruitment, whether or not recruitment goes up for all the species or only goes up for arrowtooth flounder, the main predator that we're interested in. And we ran this out from about 2017, 2018 to 2060 with a few hundred simulations for each scenario. And the management strategies we looked at are those single species estimation models, where we either estimate a natural mortality term, and some of the current stock assessments do this, or fix natural mortality to some pre-assumed value, and some of the current stock assessments also do this. And we applied a few different decision rules, harvest control rules that are used across North America and Australia, and you can see them up in the figure there, where fishing mortality changes based off of our estimated depletion. We also adapted those harvest control rules, switching out the equilibrium reference points that are currently used with dynamic reference points that account for time-varying recruitment, selectivity, and growth, just to see how those do. And we evaluate this all through a few performance metrics related to the fishery goals that we're interested in and the conservation goals we're interested in. Average catch, catch variability, whether or not we perceive the stock to be undergoing overfishing or overfished as derived from our estimation model, and whether or not the multi-species operating model defines the stock as overfished or undergoing overfishing. And one of the tricky things with multi-species models, of course, is that the reference points that we use to define overfished and overfishing aren't directly comparable to the single species models that we use for management. So in this case, we used 25% of unfished biomass as our reference point for the multi-species operating model, and the fishing mortality that got all species to that 25 SB0 simultaneously as our fishing mortality limit for the multi-species model. These are somewhat arbitrary, and we're looking in the future to evaluate different reference points, and if folks have other ideas, I'd be interested to hear that as well. So I'll go through some of the preliminary results, focus on Eastern Bering pollock, because that's the kind of big fish in the sea. And each circle represents a different combination of estimation model and harvest control rule, with the color representing which one it is. And the same color with the triangle represents the harvest control rule and estimation model, with switching out the equilibrium with dynamic reference points. And here are the performance metrics for pollock in the Eastern Bering Sea for our fishery goals. And in the upper left, we have average catch, and you can see that some management strategies lead to higher average catch, while some lead to lower. And this is mostly due to whether or not we estimate M, or natural mortality, in the estimation model. And similar trend in the upper right with interannual catch variability, with not much difference between the triangles and circles, the equilibrium and dynamic reference points. But in the lower left, kind of the main thing I think is important is that the probability of the fishery being open is always 100%, which is exactly what we want. The fishery isn't closing when our operating model is multi-species, and so we're meeting our objectives there. And then when we look at our conservation goals, similar, the triangles and circles represent the EM HCR combo. When we look at the operating model, the multi-species operating model, the probability of undergoing overfishing or being overfished is very low, if 0. So I switched these up, so higher numbers are good and lower numbers are bad, and it's 100% probability of not being overfished. So we're doing great there. And then when we look at our estimation models, our perception of undergoing overfishing, there's some combinations that lead to some perception of overfishing, but not a whole lot, so we're doing okay there. And generally, we're not perceiving the population to be overfished, so we're doing good there. And this is a plot of the terminal depletion of the operating model in both for pollock in the Bering Sea and Gulf of Alaska for each of the 5 different climate scenarios that we evaluated. The dotted blue line indicates that terminal spawning stock biomass depletion is at 40%. And as you can see across the 5 different climate scenarios for both the Bering Sea and Gulf of Alaska, all the circles and dots are above 40%, which is the current kind of target reference point we use in Alaska. So I think we're doing really good here. The stock isn't depleted when we're using single species management, and the operating model is multi-species, and there's some sort of climate. So I think summarizing all this work, I think overall single species management is achieving our objectives. We're not overfishing the stock, we're not having the stock being overfished, at least in how we defined it in this case. We also perceive not to be overfishing and not to be overfished, which is great. The fishery is open, and we're not depleting the stock terribly. So we're doing really pretty good with single species management. And I think comparing some of these different single species management strategies, there were some kind of takeaways. I think the tiered harvest control rules tended to do better. Estimating natural mortality can better approximate the population scale of the multi-species model, and this isn't kind of something new. I think a lot of simulation studies have shown estimating natural mortality is the way to go. And I think the dynamic reference points in this case didn't really improve performance, but there's no stock recruit curve in our operating model, and we don't have time-varying growth in our forecasts. So this is something we're looking to add on in the future, and I think will kind of lead to differences in our performance of those dynamic reference points. And I think there's also some big uncertainties in future research, and this is kind of where I'm really interested in taking this sort of stuff. I think there's hundreds of simulation studies on selectivity and in single species models. And I think there needs to be a lot more work on evaluating the bias and kind of management performance of single species management under different forms of species interactions, whether there's bottom-up forcing, different kind of top-down predation functional forms. I also think it's kind of hard, it's hard to compare single and multi-species models, and so I think thinking of ways of different reference points we can use for this work is important, and also maybe ways that we can better compare these sorts of models. And we also didn't look, in Alaska, some of the stocks, especially arrow-toothed flounder, are underutilized, and we didn't really look at that in this case, and I think leaving more predators in the system may impact our results, and so we're interested in that in the future. And unfortunately, I couldn't get to multi-species harvest control rules because having model issues, but hoping to get into that in the future. And yeah, this work's been supported by some wonderful collaborators and at NOAA and the University of Washington. And with that, I'll take any questions.
Questions for Grant?
Thanks a lot. So I was just wondering if the three stocks are actually taken by different fleets, or is it the same fleet? Because if it's different fleets, these species interactions might actually also have a kind of trade-off in terms of fairness. So like which stock to manage how, and which fisheries is going to profit from it?
Yeah, there's so each stock is, at least how we have it set up, is set up by separate fleets, and some of the stocks are set up or fished by multiple fleets. I think it would be super interesting to look at, we've thought about this as incorporating kind of economic reference points to get at sort of those interactions of, well, maybe we could, arrow-toothed flounder is not worth a whole bunch, but pollock's worth more, so maybe they'll prioritize fishing arrow-toothed flounder to make more money by fishing the more expensive pollock, and also possibly looking at some other different reference points that won't go into. Maybe, yeah, if that gets at it.
All right, thank you very much, Grant. I think is it quick?
Yeah, it was on the P-star harvest control rule. Just how do you move the uncertainty from your assessment into that, into defining how the P-star rule works?
The sigma, I use the sigma prescribed from the Pacific Council for either round fish or flat fish, and so I take that out of their management plan rather than the assessment itself, because it seems how they do it out there.
Yeah, I was wondering if.
Thank you, Grant.
Sweet.
Thank you. So we are over time, and so I don't want to keep you, but we are breaking, so you'll have an opportunity to catch John right outside the doors when we wrap up. I do want to take the opportunity to thank all the speakers, thank all of my co-conveners who couldn't be here today, and also those who were stuck in session 8 all day. And thank you all for coming and attending. We really appreciate it. Have a good meeting.